Hi, and welcome to a new lesson from Easy Chemistry. This is Mr. Kusai, and today we're going to have a new lesson. It's Introduction to the Molecular Shapes and Molecular Geometry. Today we're going to focus on the VSEPR model theory as well as the hybridization. Our objectives for today are to summarize the VSEPR model theory and to predict the shapes and the angles of the molecules. Let's take a look at this image here. For example, when you tie two balloons together, they will take the shape linear. Three balloons, the shape will change and it will become trigonal planar. And when we tie four balloons, the shape will be tetrahedral. Similarly, for the molecules in the space, we have the linear, we have trigonal planar, we have tetrahedral. So let's check first what is VSEPR model theory. VSEPR model theory, it's an abbreviation for the valence shell electron pair repulsion. So there is repulsion between the valence shell electron pairs, whether they are bonded pairs or unbonded pairs, shared or lone pairs. So based on the arrangement of the electron pairs that minimizes the repulsion, we need the repulsion between those pairs to be the minimum of the shared and unshared electron pairs around the central atom. So the most important thing here is the central atom. We always study the central atom. Before we continue about the molecular shapes and the VSEPR model theory, we need to have an idea about the hybridization. Hybridization, we're going to study it in details in the following videos, but to better understanding the geometry and the shapes, we need to touch the hybridization. Hybridization is mixing two or more atomic orbitals to form new set of hybrid orbitals. So it's basically overlapping two or more atomic orbitals, could be S and S, could be S and P, could be SP and D, in order to form a new set of hybridization. For example, let's check the carbon atom. Carbon atom, it has 6 electrons. The atomic number of the carbon is 6. And the electron configuration is 1s2, 2s2, and 2p2. I recommend you guys to revise my videos about the electron configuration if you have some doubts how you do them. In the energy levels, we know that the 1s has the lowest energy level, and then 2s, and then 2p. This is the second energy level, n equals to 2. Therefore, the valence electrons for the carbon are 4 valence electrons. Now, what happens when the carbon is bonded with 4 hydrogen atoms? Each hydrogen atom, it has only one electron in 1s. So 1s1, 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 and 1s1 for the 4 hydrogen atoms. And if you check here for the carbon atoms, we have 2 electrons in 2s and 2 electrons in 2px and 2py, leaving 2pz empty. So we have here 4 bonds, 4 shared pairs, we call them, because the pairs here, the pair of electrons are shared between the carbon and the hydrogens. So we have 4 shared pairs. So we have 1 electron from the hydrogen, will go here to 2px, and we have 1 electron from the other hydrogen to 2px. So now we have 2 electrons. And then this orbital is empty, so we have 1 electron from this hydrogen and 1 electron from the last hydrogen with an opposite spin. But actually, if this was the bonding, it's incorrect, because here now we have the valence electrons. We have 2 electrons in 2s with lower energy, and we have 6 electrons in 2p with higher energy. So the bonds are not equal, but actually they are equal. So this one is incorrect. What happened is, there is something called hybridization. What happened is 1 electron from S will promote to 2p. So 1 electron from 2s will promote to 2p. making 4 hybrid orbitals. If you check them, you will see that now you have 1 orbital, 2 orbital, 3, 4, and all those orbitals in terms of the energies, they have the same energies, as you can see. Now, each hydrogen atom can put its electron in this hybrid orbital. So, what is hybridization again? Hybridization is mixing 2 or more atomic orbitals, just like what we saw, S and P in this case, as an example, to form a new set of hybrid orbitals. Now, if you check here again, how many hybrid orbitals do we have? We have 1, 2, 3, 4 hybrid orbitals. And they came originally from S and the 3p orbitals. So basically 3 atomic orbitals, they form, 4 atomic orbitals, they form 4 hybrid orbitals, and they are S, P, P, and P. That's why it's sp3. We have many types of hybridization. We're going to study it in details when the time comes. Let's now go back to the VSEPR model theory. The VSEPR model theory, it's based on the arrangement of the electron pairs that minimizes the repulsion of shared and unshared pairs of the central atom. So we need to focus on the shared pairs, the number of shared pairs, and the number of lone pairs in the central atom. For example, we're going from now on to give the central atom, for example, this is C, the central atom. We're going to give it the letter A. And we're going to give the shared pairs the letter B. So in this case, we have A, because 1 central atom, and we have 4 shared pairs. That means it's going to be AB4. So the first example here we have AB2. That means we have 1 central atom, and we have 2 shared pairs. So the number of shared pairs are 2. As you can see here, this is the central atom, A, and we have 2 shared pairs. We give them the letter B. So the total number of the pairs are 2, because we have 0 lone pair. We don't have any lone pairs on the central atom. We only have 2 shared pairs. And the shape in this case will be linear, because linear will minimize the repulsion between the shared pairs. 180 degree is the maximum. And the hybridization is SP. For now, I want you guys just to understand it like this, because we have total pairs of 2. That means we need 2 hybrid orbitals, SP. If we have a 3, so it's going to be SPP, so SP2. If we have 4, it's going to be SPPP, so SP3, hybrid orbitals. Now, as an example is the beryllium. We don't care about the terminal atoms, which are Cl and Cl. So beryllium, Be, from the periodic table, you will find the atomic number is 4, and the electron configuration should be 1s2, and the valence electrons are 2, because 2s2. We have 2 electrons in 2s. And also we have 2p, which is 0. That means no electrons in P. If we check the hybridization, you will find that in 2s, we will have 2 electrons. And then in 2p, the higher energy, we have 2px, 2py, and 2pz. Similarly to what happened to the carbon, we need to have hybrid orbitals so that all the bonds are equal in the angles, in the energies, etc. So one of the electrons in S will promote to 2px, and it will become like this. We have 1 electron in S and in P, so it's going to be two hybrid orbitals with two electrons, singles, and this leaving 2px and 2py as atomic orbitals. So 2py and 2pz, and they are empty. Now here the hybridization is only s and only one orbital from p, so it's going to be sp. As I told you, we will have a better idea in the next videos about the hybridization. Now, the other class, for example, is when A, the central atom, has three shared pairs, B3. So it's going to be A in the center with three B's, because B is the shared pair. As you can see, the lone pairs are 0, so the shared pairs are 3, lone pairs are 0, so the total pairs should be 3, and the shape will be trigonal planar. It's just like when you tie 3 balloons together. It's going to take the shape of trigonal planar. Now, let's summarize these two shapes, the AB2 and the AB3. And of course, AB3, we have 3 total pairs, and the hybrid orbital should be spp, so it's going to be sp2. So whenever we have 2 bonds like this, it's going to be sp. When we have 3 bonds, total bonds or total pairs, it's going to be sp2. If you check here, this is, for example, the central atom, which is A, and we have 2 lone pairs, two shared pairs, and this is the geometry of the molecule in space, as you can see. It's going to be linear to minimize the repulsion between the shared pairs. The molecular geometry is linear, and the bond angle is 180. All right. Now, for the AB3, so I'm going to add one more bond, and it's going to be trigonal planar, and the hybrid orbital should be sp2 because we have total number of 3 pairs, so it's going to be spp sp2, and the angle between the bonds is 120. All right. The third class is when we have AB4 now. In AB4, we have 4 lone pairs, 4 shared pairs, 0 lone pair, so the total number of pairs are 4. So the hybrid orbital should be s, p, p, and p, so it's going to be sp3. And the shape is tetrahedral. Let's check the shape. This is the shape of the tetrahedral, and the angles between the shared pairs are 109.5. We need to memorize these angles. A lot of questions come in the exam about the angles. So as you can see here, the shape is tetrahedral. We have A and B4. The hybridization should be sp3. Let's have an example. If you check here, we were talking about the methane, which is CH4. So this is the central atom, and we have 4 shared pairs, so it's going to be AB4. Let's check the AB4, and let's check the hybridization for this compound. As an example, CH4. And the carbon from the periodic table, it has 6 electrons. So 1s2, 2s2, and 2p2. If we're drawing the 2s, this is the 2s with 2 electrons initially. And for the 2p, we have 2px, 2py, and 2pz, with 1 electron in 2px and 1 electron in 2py. So what happened here is 1 electron from S will be promoted to 2pz to give you 4 hybrid orbitals, just like this. And these hybrid orbitals are sp3, because we have one s or one orbital from s and three orbitals from p. Each one has single electrons, and the four hybrid orbitals, they have the same energies. Now, with all the hydrogens, with the four hydrogens, each one has one electron, can go to these hybrid orbitals. All right. The class AB5, it means that we have a central atom of A, and we have 5 shared pairs. No lone pairs. All of them, all our examples for now, we are studying no lone pairs. The number of lone pairs on the central atom are 0. So this one also we have the shared pairs 5 and the lone pairs 0. So the total pair are 5 pairs. When we have 5 pairs, we need 5 hybrid orbitals. They are S, P, P, P. So that's sp3. And we need one more from D. So it's going to be sp3d. This is the hybrid orbitals. So when we have AB5, the shared pairs are 5, the lone pairs are 0, and the shape should be trigonal bipyramidal. Don't make a mistake between the trigonal bipyramidal and the trigonal planar. Trigonal planar, we have only 3 shared pairs, and the hybridization is sp2. But the trigonal bipyramidal, the hybridization is sp3 because we have 5 total pairs. And we have the 5 total pairs are shared, all of them. We don't have any lone pair. Last class about the shared pairs without lone pairs, when we have AB6. In the AB6, the shared pairs, of course, we have 6 shared pairs, we have 0 lone pair, and the shape will be octahedral. And we have here only one type of the angles. All of them are 90. See, all the angles here between the bonds are 90. But here in the trigonal bipyramidal, when we have AB5, the angle between these two is 90, but the angle between these two is 120. When we have AB6, that means we have 6 shared pairs, 0 lone pairs, so the total pairs are 6. The shape is octahedral, but the hybridization now is S, P, 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 D, D. So it's going to be SP3D2. Let's have a look at when we have 5 pairs. This is 5 pairs, and as you can see, the angle between these 2 pairs is 120, but the angle between these 2 pairs now, it's 120. So it was 90 here between these 2, and 120 between this one and this one. This one we have AB5, and the shape is the trigonal bipyramidal. Last one, when we have AB6, it's going to be all of the angles are 90s between all the shared pairs. And the molecular geometry, we call it octahedral. All right. So AB6, octahedral, hybridization is sp3d2. Now, what if we have shared pairs, but also we have lone pairs? We gave the letter A for the central atom, and we gave B for the shared pairs, now we're going to give E for the lone pairs. All right, for the lone pairs, for example, also they occupy space. They take space, and also they do repulsion with the other lone pairs and with the shared pairs. So in this case, AB2E, we have 2 shared pairs, and we have 1 lone pair. It's on the sulfur, on the central atom here. And the shape is no more linear. See here, if you check this shape here, this molecule, it doesn't have any lone pair. The lone pair was 0. But once it has one lone pair, this lone pair also will push the shared pairs down, and it will have it as a bent. And now, what is the hybridization? Let's check. The shared pairs are 2. The lone pairs are 1. So the total pairs are 3. So it's going to be 3 total pairs. SPP, that's SP2 for the hybridization. Let's check how we solve this example. If in the exam they ask you predict the shape of SO2, how can we do it? The first step, we need to decide which one is the central atom. As you can see, the central atom is S, because oxygen now here are terminal atoms. So we need to write the electron configuration for the sulfur, which has 16 valence electrons. So it's going to be 1s2, 2s2, 2p6, 3s2, and 3p. How many electrons so far? 10, 11, 12. We have 4 electrons in the outer shell, in the 3p, but the valence electrons are 6. This is the first step, writing the electron configuration. Step number 2 is to decide how to write the Lewis structure for the sulfur. And Lewis structure also, guys, I recommend you to watch the previous video about Lewis structure and how we write it for the atoms. So this is the sulfur. We have 6 valence electrons, so it's going to be 1, 2, 3, 4, 5, and 6. Now we have oxygens as terminal atoms, not central atom, and we have, for each oxygen, we have 6 valence electrons. We know it because oxygen, it has 8 electrons, and the electron configuration is 1s2, 2s2, 2p4. So it has 6 valence electrons. Now we have here double bond with this sulfur. We also have double bond with the other oxygen because it has 1, 2, 3, 4, 5, and 6. Now here the sulfur has 1 lone pair. So we have here shared pairs, and we have 1 lone pair. Before we continue, guys, the double bond and the single bond, we treat them as a single bond, the double bond and the triple bond. So here we have double bond, it doesn't matter. It's only 1 pair, we call it. And the other one also, it's a 1 pair. So the shared pairs now we have, because we have double and double, we consider it as single. So the shared pairs are 1, 2, but the lone pairs, we have 1 lone pair on the sulfur, and this 1 lone pair, it will push the 2 shared pairs. And that's why the geometry is going to be bent, not linear anymore. Let's have an example here. For example, if I have, this is the BeCl2 without any lone pair. If I'm going to add 1 lone pair, what happens is the lone pair will push away the 2 lone pairs, and the molecular geometry will be bent. Let's check the angle, the bond angle. It's 120 because we have only 1 lone pair. All right. Class AB3E now. And AB3E, we have here 1 central atom, A. We have 3 shared pairs, and we have 1 lone pair as E. And as an example, it's NH3. The shape is trigonal pyramidal, not trigonal planar, not trigonal bipyramidal. It's called trigonal pyramidal. and the hybridization should be sp3. Let's check why is it sp3, because the total pairs are 4. So we need S, P, P, and P. That's sp3, the hybridization. Now, let's take this example, the NH3. Nitrogen from the periodic table has 7 electrons. So it's going to be 1s2, 2s2, and 2p3. That is the valence electrons are 5. So I'm going to write the nitrogen has 5 valence electrons. 1, 2, 3, 4, and 5. And we have only 3 hydrogens, so each hydrogen has 1 electron. And these are the single bonds between the 3 hydrogens and the nitrogen atom. That means we have here in this case, we have 3 shared pairs and we have 1 lone pair. If we check the geometry here, if I have 3 shared pairs, as you can see, this is the nitrogen in the center, 3 hydrogen atoms, and this is 1 lone pair. You will see that the geometry is going to be trigonal bipyramidal. Trigonal pyramidal, as you can see. All right. Don't forget that the hybridization is sp3 because we have 3 shared pairs and 1 lone pair. That are 4 total pairs, and we need S, P, P, and P. Last example for today, it's about AB2E2. That means we have 1 central atom, we have 2 shared pairs, and we have 2 lone pairs. As an example about this is the water, H2O, oxygen. If we need to write the atomic number, the electron configuration for the oxygen, it has 8 electrons, so it's going to be 1s2, 2s2, and 2p4. That is the valence electrons are 6 valence electrons, I mean. So oxygen has 1, 2, 3, 4, 5, and 6. Those 2 electrons are bonded to the hydrogen, 1 and 1, leaving those pairs are lone pairs. So basically we have 2 lone pairs, we have 2 shared pairs, and we have the central atom, which is A. So it's going to be A2, AB2, E2. Because we have 4 total pairs, 2 lone and 2 shared. That's why we need 4 hybrid orbitals, S, P, P, and P. They're going to be sp3. And the shape in this case is also bent, just like SO2 when we did S double bond O, S double bond O, and here we have 1 lone pair. Don't forget, in this molecule, the angle, it was 120, but in the water molecule, we need to check the angle. When we don't have 3 shared pairs, we only have 2 lone pairs and 2 shared pairs. As you can see here, this is the molecule, and the angle between them is 109.5. See? So the angle between these shared pairs is 109.5. I will make, guys, a summary for this lesson later on to put all those classes in one table. It's better for revision and more understanding. In next lesson, guys, it's very important. We need to talk about the hybridization for each, and I hope you guys you learned something new. If you have any question, just write it in the comments. I will read all the comments. Or if you need more focus about the problem solving, feel free to hit me up in the comments. Have a nice day. Bye bye.